In this video, we're going to talk about power rules or exponent rules. So let's take a look. A power, a to the power m, is really a shorthand of writing a multiplication of the same number over and over. A times a times a times a, m times. Now, obviously here, if you can write like that, m is a positive integer. So for power at the beginning, a to the power m is really a definition, is a shorthand, is a way of mathematicians save time, save writing. This is very similar to the idea of multiplication. We know that we have a plus a plus a m times, right? It's very cumbersome to write this way, and we define a multiplication. This is like a times m. MA's multiplied together, MA's adding together is written can be written as m times a or a times m. So a to the power m is really a shorthand, and this is the definition: a to the power m, a times a times a, m times. So with that, we can derive a few properties just from this definition. Property number one. We say a to the power m times a to the power n is going to equal a to the power m plus n. Why is that? We can use the definition to verify this very easily. Remember, a to the power m, this is a times a times a m times. Now this is a times a times a n times, and they are multiplied together. So I multiply here. Now, by the basic associative law, or actually just by the definition, a to the power m, this is m plus n a's multiplied together, right? So this is exactly equals a to the power m plus n. Very easy to remember this. Now, property number two. How about a to the power m divided by a to the power n? Now, at the beginning, we can think about m is bigger than n, and both are positive integers. And later, we'll see how we actually remove this. This, by definition, a to the power m equals a times a, ma's multiplied together. I'm going to put the ma's here. And a to the power n is a times a times a, and a's multiplied together. So since we have more a's in the numerator than the denominator, we're going to cancel all those na's from the numerator. We still have a bunch of remaining. How many remaining? It will be a times a, like that, m minus n, a's multiplied together. So this, by the definition of this, is equals a to the power m minus n. So, okay, I'm going to put the little rule on this side for people to see more clearly. A to the power m times a to the power n equals a to the power m plus n. And here, a to the power m minus a to the power n equals a to the power m minus n. Here, we're going to have this little constraint of m bigger than n. Okay, property number three. How about a to the power m times b to the power m? Now, in this power definition, this is called, a is called the base, and m is called exponent. So property 1 and 2 are basically saying the base are the same, have different exponents, and how we're going to, operate on the exponents. Here, property 3 is the base is different, exponents the same. In here, this is going to equal ab to the power m. And why is that? If you expand a to the power m, m(a)'s multiplied together, this is m(b)'s multiplied together. So let's write it. A times a, m(a)'s multiplied together. This is b times b, m(b)'s multiplied together. If we use the associative law and the commutative law, this is the same as a times b times a times b times a times b, m such things multiplied together. This is, of course, equals ab to the power m by definition. So a to the power m times b to the power m equals ab to the power m. Okay, these are the three properties so far. Let me move to the next page. Now, property number 3. This is a bit of a tricky property. A to the power m raised to the power n. What is this equal to? Some people might think this is equal a to the power m to the power n. This is definitely not true. This is not true. Instead, this equals a to the power m times n. So you have a power raised to another power. If you're doing the power first, raised to another power, this is the exponents just multiplied together. And how we show this? A to the power m to the power n is equal, this whole thing is equal. First, let's think about a to the power m to the power n is equal a to the power m times a to the power m times a to the power m. This is n times, right? By definition, a to the power anything m is equal a m times together. So in here, if you treat a to the power m as this little a, and then raise to the power n, you have a to the power m times a to the power n times. That's the definition of this. But each of the a to the power m is itself is a times a m times, and then a times a m times. Each of these, okay? Each of these is this, and like so on. So a to the power a m times. And of course, the original, there's n times of such things multiplied together. So now if you count the number of a's there are a, m times n such a's, which is by definition a to the power m times n. So here, I want to say a few words about this property. So just look at an example. Let's say example 1. Let's look at 2 to the power 3 raised to the power square. This is going to equal 2 to the power 3 times 2, which is 2 to the power 6, which is equal to 64. On the other hand, if 2 to the power 3 raised to the power 2, then by the order of operators, one can do this power first, which is 2 to the power 8, which is equals 256, which is much bigger than this number, right? So just be careful. When you have raised to the power and then raised to another power, the exponent just multiply together by this property. So in here, we have 4 properties. I'm going to just put them together so we can review for yet another time. Property 1, a to the power m times a to the power n equals a to the power m plus n for both m and bigger than 0 positive integer. Property 2, a to the power n divided by a to the power n equals a to the power m minus n. Here is for m is bigger than n, positive integer. The third one is a m times b to the power m for 2 different base with the same exponent is going to equal, you can combine the base raised to the same exponent. Property number 4, a to the power m raised to the power n is going to equal a to the power m times n. This is a property that you should try to memorize and, of course, first understand and memorize this. Now in here, we are putting this constraint of m and n are both positive integers. And this is really for a intuitive understanding of this powers and actually where it comes from, right? Here, we're going to extend this one to non-positive integers. First, let's look at how we define a to the power 0. What does that mean, a to the power 0? You know, it's very hard to imagine that 0 a's multiplied together, right? Now, to define this, the rationale of defining this is we're going to see what property this has to hold to make the properties above still true. If we let property 1 to be true for n equals 0, then we know that a to the power m times a to the power 0 is going to equal a to the power m plus 0 equals a to the power m. Now you see a to the power m times a to the power 0 equals a to the power m. This is really forcing that a0 has to equals 1 if we want this property 1 to be true for any m and n, right? So this is 5. We call it a property 5. This is more or less a definition of extending the power definition. A to the power 0 equals 1 for any a. And here, there's really something weird going on. 0 to the power 0, we still define as 1, even though this does not really make a lot of sense. Well, if you add this property into math, you're going to save yourself a lot of trouble. So this is really a kind of a definition. It really does not have much of mathematical meaning other than this adds a lot of convenience. Now, property number 6. How about a to the power negative n for n positive? So we're talking about negative power, negative exponent, n bigger than 0. How we define a to the power n minus n? Again, we define this by enforcing or hoping that the property 1 or 2 or 3 or 4 true for any mn. Now, if property 1 is true for negative n, so then let's choose one particular mn n, okay? A to the minus n times a to the power n is going to equal a to the minus n plus n is going to equal a to the power 0, right? A to the power 0 we already defined as 1. So we see that a to the negative n times a to the power n is going to equal 1. That means a to the negative n and a to the n are reciprocals. That's the definition of reciprocal. So which means this is equivalent to say a to the negative n is equal 1 over a to the power n. Well, now this is something that makes intuitive sense. A to the negative n is 1 over a to the power n. So to calculate negative exponent, well, we can just calculate the positive exponent and doing the reciprocal of it. So that has all the properties of power rules.